All right, so we've got this problem here. For those of you online, we went over this a bit on Friday too. It's available online. All right, so what we're doing here, we're working our way through this. So from A to B there, we basically did a work energy analysis. We got 40 meters per second. And then A contacts B, all right? So what we have here, I guess just to review, is we've got this action occurs on a flat table. So these objects are not changing elevation at all. They're just sliding on a flat table. We've got A slides and contacts B. B is in a channel there, so is constrained to move only in the X direction. So when A runs into B, they're going to stick together. You know, A will embed itself in B, and then AB will move in the X direction. So notice that A comes in at a 30-degree angle. So A is going to slow down a bit by the time it gets to B. Then when it sticks in B, AB will slide down that channel in the X direction. And so you're going to have to work a bit with trig and momentum analysis there to get that velocity of AB just after the collision. Then what's going to happen after that is AB will slide down the channel. It will experience more friction on the surface there. We're going to ignore any friction from the walls. And then AB will hit C. And when AB hits C, the whole assembly there will start to pivot or rotate, I guess, about point O. All right. So what we want to do is track this thing through. It's rather different than work energy. In work energy, we just looked at the beginning point and the end point and the work that occurs in between. Here, we're going to have to analyze each little transition point. So we're going to go from A as it slides from A to just before hitting B. Then we're going to look at the velocity of AB as it starts moving down the channel. Then we'll look at the velocity of AB just before it strikes C. And then we want to get to that next step. Now the next step is, we've covered it a bit in the homework. It's kind of that transition there between linear and angular momentum. Okay, so that's the idea with that last step. And this is probably the tricky one, you might say. Although I think, the mathematics on it isn't really all that difficult, but the concept of it might be a little bit. So what we have to do on this thing is in this last step, when AB is just about to strike C, we have to realize what's going to happen there is the whole assembly, ABC on one side and D on the other, are going to rotate, is what they're going to do. So we have to have some means to figure that out and deal with that, okay? So what we are going to do then is we're going to look at that motion right there when the whole assembly, ABC on the bottom and D up on the top, are all rotating together. So there's kind of two elements of this to consider. One is, right now, that's linear momentum on AB. But just as soon as it strikes C, it turns into angular momentum. So you have to have some way of dealing with that. And there was some of the stuff in your homework that kind of covered those concepts, okay? So hopefully you looked at that this weekend. Kind of that transition from linear to angular momentum. Okay, so we've got this thing and it's about to hit C. So right now, that's linear momentum on AB. But as soon as it hits C, it changes into angular, all right? So now it's angular momentum. This whole assembly is spinning. But the issue on this is going to be not only is ABC down here spinning, but D is also. And D has a different moment arm, you might say, or whatever you want to call it, a different length there than does ABC. So you have to kind of deal with that some way. And the thing to understand about that is that the length of the moment arm affects, so the radius length or length of the moment arm, whatever you want to call it, affects the velocity of the endpoints. So if I'm taking this ruler here and spinning at about a point not in the middle, look at the relationship between the velocity here and the velocity there. They're not the same, are they? The V of the ends of this ruler are not the same. So you got to figure out some way to work through that. And again, the concepts, maybe the more difficult part, the mathematics of it are pretty simple, but you do have to get the concept. You got to deal with that somehow. that the velocity of ABC does not equal the velocity of D. Okay, that's kind of the issue here. V, velocity meaning V, the variable V, okay, which is part of the angular momentum equation there. All right, so that's kind of the deal with that. Do we got any questions on that bit, on any of that?
So both points complete the circle at the same time, right?
They both rotate together. Yeah, you're right. They would both turn one revolution.
So you can set them equal to each other that way, and it's like, and then sort of.
Yeah, you got to figure out some way to incorporate all this stuff into one big equation, and it's not that horribly difficult mathematically, but it's the concept of it that I'm trying to get across. Okay. And you have to kind of just figure out how to kind of combine all this stuff together to make one thing out of it. Okay. So, we got any? All right. So kind of work your way through. Why don't we take another, 15 minutes on it or so, and see what you can do with this. So, some of you are right to where that collision is about to happen. So, that's kind of where I'd like to get. This will probably be due Friday, I think. Okay. All right. For those of you online, I'll pause it here, but let's see. So we've got that far so far. So you want to be getting to that velocity of AB just before it strikes C. And then we'll check in on that. And then we want to look at how this whole thing starts to rotate. This is what we want to do. All right. Couple things on this that have come up just talking to people. I do want you to be working through this, and you're getting to that place where right about where AB is about to hit C, and you're getting a little hung up, and that's fine. I mean, that's kind of the idea behind creating this problem in the first place, is to have you work through that. Okay, so what we've got here is we've got the velocity of AB just before striking C. So that's, what is that? That's about 8.17, right? I can't find my pen. Okay, so you ought to be getting 8.17. That's AB just before it strikes C, okay? Okay, now, what's happening here when that thing strikes is you've got some angular momentum going on, and more particularly, what you've got is conservation of angular momentum. So what you have happening here is right before that AB strikes, you want to look at its angular momentum. All right, right there. You want to know what's the angular momentum of AB coming in, and then you're going to relate that to how it distributes across A, B, C, and D after it strikes C. Okay, so a good starting point on this, I think, would be to look at this angular conservation of angular momentum equation. Okay, now the moment zeroes out. And what you get then is this. So D1 mv1 equals D2 mv2. Look at this for AB. That's probably a good place to start. What is the angular momentum of AB as it comes in and it's about to strike C? But just before it strikes C, what's the angular momentum of AB? All right. And the reason I told you we look at this on Monday is because I was thinking maybe over the weekend you'd be looking at some of this other homework. And you see similar ideas on this that will help you grasp this on this problem here. A similar thing there on 261. You've got that mass coming in, and you're about to have it hit that armature, and the whole system's going to start to rotate. So somehow you have to relate the angular momentum of the mass just before it strikes, okay? So the angular momentum is dmv, right? Now, look at that thing and just fill in as best you can what's D, what's M, and what's V. Just look at those three things separately. And some of them are right on the sketch. So fill in those numbers if you want to look back at this one to help you get started on it, okay? We've got a similar thing, maybe not quite so much here. That's probably the best guide to doing this thing, all right? But for this one, once again, fill in those three things for AB. What's the offset distance? What's the mass? And what's the velocity? Okay, that's where I would start on this if I were getting hung up on it. Okay. All right, so that's the basic idea on this thing. It'll be due Friday, and we'll cover it a little bit more perhaps Thursday, I think. Okay, so that'll looking like it'll be due Friday.